Hi everyone. Today we will discuss the materials and properties. First is that we should know what is concrete. Concrete mix or its ingredients are usually composed of air, Portland cement, gravel or crushed stone, that is coarse aggregate, sand or fine aggregate, and water. Normally, the typical mix is around 10 to 15% of the cement, 15 to 20% of water, 60 to 75% aggregate, 5 to 8% entrained air. For further study about the concrete, there are two recommended textbooks for further reading. You can read the Concrete by Mindness, Young, and Darwin, and the Concrete Microstructure Properties and Materials by Meta and Montero. If we look at the concrete from different levels, it is actually a multi-scale material. As you can see at level 0, the calcium silicate hydrate, this is in nano scale. But if we have to go up the level, that is level 1, the CZ metrics, you can see the CZ solid plus the pores. And for level 2, that is for the cement phase is just cement plus water. So it will show us the CZ metrics plus other hydration products and unhydrated clinker. To the engineering level, that is level 3 concrete, you can see the cement phase and aggregates. So for this reason, the concrete is really a complex material to study. So that is why most of the researchers in cement and concrete, they try to divide this into 4 levels so that it would be easier for us to understand what's going on concrete. Also, we have the proportioning of concrete mixes. It is important to proportion the concrete mix so that we can get the desired strength that we need. We can use the design and control of mixtures. You can use the ECI standard 211.1 for normal weight, heavyweight, and mass concrete, or the ECI standard 211.2 for structural lightweight concrete, and the ECI standard 211.3 for no slump concrete. Here is a diagram. It's a simple beam actually. By changing the mid-span portion of the beam with a coiled spring at the bottom and a rubber at the top, and assuming that at the center or the neutral axis is a hand support. So if we have to apply a load, there will be some movement. So when a load is placed on top of the beam will bend at the hands joint. So this bending tends to close the gap at the top where the piece of rubber is inserted, and to make the gap at the bottom widen where the coil spring is inserted. In other words, the rubber will be compressed while the spring will be stretched. The spring will receive a falling strain and have the tendency to resist the bending. So this is the simplest diagram that shows how tension side and the compression side of the beam actually can be determined. It's very important that you know that if you apply vertical load, where is the location of the tension side, because the tension side will crack and that portion needs the steel reinforcement to reinforce the given section. We have another illustration here. Actually, this is a planks or boards before and after bolted together. What is the effect of the reinforcement in the concrete beam? As you can see, the top portion without the bolts. If you have to apply a loading at the top, then these planks, which are supported only at the ends, will actually slide each other. So as you can see, there will be some sliding. But if we have to apply a bolt, if the planks or boards are bolted together, assuming that it is made of stirrups, or we can assume actually that it is stirrup, the slipping can no longer occur in this particular case. So it's very important that you will see the effect of the stirrups. The stirrups will really help so that the adjoining planks or cords will not slip together. This phenomenon is actually due to shear. So the shearing will slide its plank or board. So what is reinforced concrete then? By definition, reinforced concrete, or RC in short, is a combination of concrete and steel wherein the steel reinforcement provides the tensile strength lacking in the concrete. As you can see in the figure below, the top portion is in compression and the bottom is in tension, where the cracks starts at the midspan of the beam and it propagates upward. At the same time, cracks towards the supports will also form as we continue to increase the loading P at the midspan. As you can see in section A, you can see the steel bars applied at the tension side of the section and the neutral axis and the compression side of section. Also, we have the concrete cover. Concrete cover is very important in reinforced concrete because as we know, the concrete is porous and we try to provide thicker concrete cover so that there will be no corrosion of the reinforcement. Take note that corrosion of reinforcing steel will only occur if there will be air and moisture coming from outside. So to prevent the corrosion of reinforcing steel, we need to put concrete cover. And take note, when iron plus oxygen will become iron oxide, the volume of the rust will actually increase. And this is the reason why as reinforcing steel is corroding, concrete cover will also spoil. It will crack and then spoil. And that's the main reason that as the reinforcing steel is exposed to the air, then there will be an accelerated corrosion on the steel, which should not happen. In using the reinforced concrete, we need to know the advantages of it, why we use reinforced concrete. Of course, concrete is cheaper than steel, and there is durability from concrete covering and continuity from monolithic joint, and also concrete and steel are good combination. The steel and concrete has a very good bonding. It prevents slip of steel bars. The concrete covering prevents water intrusion and bar corrosion. And at the same time, the steel and concrete has similar rates of thermal expansion. What does it mean? If the steel will expand due to high temperature differential, then the concrete will also expand. But since the two materials have the same rates of thermal expansion, then they will just expand at the same time or kulo siya at the same time. But aside from the advantages of the reinforced concrete, there are also disadvantages on it. Why? Number one, the construction time. It really takes time to construct using reinforced concrete. And at the same time, the concrete quality control. The properties vary widely due to the proportioning and mixing. It's not easy to control the quality of the concrete, especially if you have different laborers or persons to operate the mixing. So it's very important that those who are mixing the concrete should be able to do the same quality of the concrete. But of course, it's really difficult. That's why this is the weakest link, one of the weakest link of reinforced concrete. Aside from that, there will be cracking of concrete. Also, concrete is very low, or it has a very low tensile strength. Concrete is only good in compression, but really weak in tension. Aside from that, formworks is very expensive. Normally, we can compute that the formworks will comprise around 40 to 60% of the concrete cost. So that's really expensive. So most of the time, we will really look into this weakest length and look for a solution so that we can minimize the effect of this problem. Also, we have heavy and large members due to low strength per unit of weight of concrete. And last weak length is the creep and shrinkage. Also, we need to know the unit weight of concrete. We can classify the concrete into three types according to its weight. We have the lightweight, the normal weight, and the heavy weight. For the normal weight, concrete with the addition of reinforcement, normally we assume that there will be 5 PCF in addition to the weight of the concrete. So normally the normal weight of reinforced concrete is 150 PCF or pounds per cubic foot, or in terms of kilogram per meter cube, that's 2,400, or in terms of kilonewton per meter cube, that's 23.56 kilonewton per meter cube. For the lightweight aggregate concrete, you can also see here the different dry unit weight of either the low density concrete, the moderate strength concrete, and the structural concrete. Normally, the structural concrete are the expanded slag, centering grade, expanded shell clay or fly ash, and the rotarical expanded shell clay and slate. Also, we have the cementitious materials, or actually the cement. We normally call it as cement, but nowadays we normally mix with other cementitious materials, so we call it the cementitious materials. This cement is what we call a hydraulic cement. Why? Because this cement will react with water. So that is why the hydraulic cement will set and harden in the presence of water. Hydraulic cement will chemically combine with water to form a hardened mass. Also, we need to know the types of Portland cement. It is according to ESTM, that is American Standard Testing and Materials, C150. There are 5 types of Portland cement with the different uses. For type 1, this is the ordinary construction where special properties are not required. So normally our cement here in the Philippines are type 1. Also, we have type 2. This is for ordinary construction when moderate sulfate resistance or moderate heat, heat of hydration is desired. Type 3, when high early strength is desired, has considerably higher heat of hydration than type 1 cement. Type 4, when low heat of hydration is desired, and type 5, when high sulfate resistance is desired. Thinking about the heat of hydration, when water and cement are mixed together, there will be heat of hydration. It will emit some heat. So, of course, without the addition of any fire or any other source of heat, there will be heat of hydration, especially from the beginning of mixing up to around 16 hours. The heat of hydration will be increasing, and after 16 hours it will go down. So you have to be careful when using a Portland cement, because for excessive heat of hydration, your concrete will crack. So that is why when you need a low heat of hydration, you can use type 4 cement. Also, there is what we call the blended hydraulic cement. This is according to ESTM C595. Hydraulic cement is normally Portland cement type 1, but as I have said, we can add other cementitious materials. So that's why we call it a blended hydraulic cement. It can be a Portland blast furnace slag cement, so that's type 1S. The Portland pozzolan cement, that is type 1P. This is quite common in the Philippines. You will see most of your cement is type 1P because that is a Portland pozzolan cement. Also, we have the Portland limestone cement. That's type IL or 1L, and the ternary blended cement type 1T. For mass concrete and seawater construction, there are also several categories of blended hydraulic cements that can be used, such as the Portland blast furnace slag cement has lower heat of hydration than the ordinary type 1 cement and is useful for mass concrete structures such as dams. Because of its high sulfate resistance, Portland furnace or blast furnace slag cement is used in seawater construction. Portland pozzolan cement is a blended mixture of ordinary type 1 cement with pozzolan. Blended cements with pozzolan gain strength more slowly than cements without pozzolan. So take note about this one. Although it gains slowly, or the cements with pozzolan gains slowly more than the cements without pozzolan, it does not mean that it is weak. It just gains its strength slowly. Because it gains strength slowly, they produce less heat during construction or hydration, and thus are widely used in mass concrete construction. Also, the code or ECI code actually gives us compliance requirements for cementitious materials or cement. From ACI 318 Table 26.4.1.1.1a, specifications for cementitious materials follows the following. We have the Portland cement, you can follow ESTM C150. The blended hydraulic cement should be ESTM C595. So this is very important that you have to understand these different specifications. Expansive hydraulic cement is ESTM C845. Hydraulic cement is ESTM C1157. Fly ash and natural pozzolan ESTM C618. Slag cement ESTM C989 and silica fume ESTM C1240. Take note that all cementitious materials is specified in the table, and the combination of these materials shall be included in calculating the WCM or the water cementitious materials ratio of the concrete mixture. By the way, if you are reading old books and old authors, actually they are using W over C or WC. We call it the water cement ratio. But since it's quite common to blend other cementitious materials in our cement, so we call now, or ECI actually says we can now call it as WCM. So WC is the same as WCM. To see the different elements of the cement grain, you can see this pictorial representation of the cement grain cross section. Normally, the cement grain is composed of these different compounds: the C3A, the tricalcium aluminate; the C3S, the tricalcium sulfate; the C2S, the dicalcium sulfate; CEO, the lime or calcium oxide; manganese oxide; and the C4EF, the tetra calcium aluminate pyrite. Normally, the cement is composed of these three compounds: C3S, C2S, C3A, and C4EF. And the glow of the cement is normally taken from the calcium hydroxide, the calcium sulfate, I mean, or the tricalcium silicate and the dicalcium silicate. So here, the tricalcium silicate, if you have to add water, will result to calcium silicate hydrate and calcium hydroxide. Or simply in cement chemistry, this is quite different from the chemistry that we know. In chemistry that we know, C is for carbon, H is for hydrogen. But in cement chemistry, we are using what we call the oxides. So if you say capital C, that means calcium oxide. Capital S, that's silicate dioxide. H is water, H2O, and other uh, symbols using cement chemistry. So here, the equation above can be represented by what we call the cement chemistry symbol. The C3S, the tricalcium silicate plus H, that is water, will result to calcium silicate hydrate or CSH plus the calcium hydroxide or CH. How about the raw materials of cement? It's important that you know the raw materials used in the manufacture of cement. Normally, cement contains high in calcium, high in silicon, low aluminum, and low iron. So normally for calcium, we use limestone, marl, calcite, aragonite, shale, seashells, and cement kiln dust. For the silicon, we can use the clay, the marl, sand, shell, fly ash, risal ash, and slag. Also for the aluminum, we can use clay, shell, fly ash, and aluminum or refuse. For the iron, we can get it from clay, iron ore, or the mill scale or shell. The cement actually is composed of different chemical. There is a chemical composition of the cement, and you can also know its effect. So normally the cement is contains what we call lime or calcium oxide. The percentage of that is normally 60 to 65%. The lime controls the strength and soundness of the concrete. Also, we have the silica, the silicon dioxide. Normally, this is the second most abundant chemical composition in cement. It's around 20 to 25%. It gives strength. Excess quantity causes slow setting. Also, another ingredient, the alumina, that is dialuminum oxide. This is around 2 to 4%. This imparts color and helps in fusion of ingredients. Also, we have the magnesium oxide. This is around 1 to 3%. It has color and hardness, but excess causes cracking. Also, we have the sodium oxide, sodium oxide. That's around zero point 0.1 to zero point 0.5. It controls residues and excess of this amount causes cracking. Also, we have the sulfur trioxide. This is around 1 to 2%. Of course, this makes cement sound. These are also the typical compositions of the cement minerals as found in the Portland cement clinker. Cement clinker is actually it's just like a marble size particle, and we need to pulverize that one, and with the addition of other minerals, it will become cement. So we have the C3S, the C2S, C3A, and C4EF, which is composed of calcium, silica, aluminum, and pyrite. You can see the different amounts of these chemicals for the composition of cement minerals. If you look at the cement paste, that is cement with water, it will hydrate and it will become hardened in several hours. It is what we call a cement paste. I cut a portion of the cement paste, polish it, and look at the electron microscope. I use the electron microscope here. As you can see, the dimension of the anhydrous cement, the white one, is around 20 microns. And the largest, I think that's 60 to 80 microns. This is in microns. This is very small. So as you can see, the white portion is actually an anhydrous cement, meaning unhydrated cement. If you mix cement and water, there will be chemical reaction. The the water and cement will form into sea sets. As you can see, this gray colors, these gray materials is what we call the sea sets, the calcium silicate hydrate and calcium hydroxide. The calcium hydroxide is this one, this color, this gray. So as you can see, it's easy to visualize the anhydrous cement because that is white. The C-edge that is gray, and C-edge more blacker than C-edge, and the black ones are pores. This is void actually. Normally, because when you polish this specimen, we normally put epoxy, and epoxy is has no color, so it actually forms, or if you look at the electron microscope, the color is black. Okay, so this is all about the cement, and the rest of the ingredients will be discussed in the next video. Thank you for listening.